Hi guys, how are you? New day, new chapter. So today we will start chapter 7, and chapter 7 is about explainability. So basically, we're trying to explain uh, model predictions, which is a little bit different than explaining a phenomenon, like if something happens, why it happens or how it happens, versus when a model predicts something, we're trying to understand how was the model able to predict this particular prediction, which may or may not align with how a phenomenon actually happens. So as always, we're gonna have a quote, and this is if you're familiar with the boys, it's a series. It's actually very good and funny. So in one of the scenes, I believe in season one, maybe the early episodes. So translucent doesn't even mean invisible. It means semi-transparent. And I find this meshes a lot with machine learning, even especially with this chapter, because when somebody says transparent model or an explainable model, we tend to believe or we tend to think that we know everything about the model, but it's really not that transparent. It's has a little bit of a gray shade into it. So if you want to think about the machine learning pipeline, we do have a model. We do evaluate this model, and now we're somewhere here. In reality, what I would like to feel with this chapter is basically we're somewhere here, somewhere between deployment and evaluation. Because somebody could argue that you can evaluate a model through its explainability if it's explainable enough or not, which I tend to agree with to some degree. But somebody could also argue that, after the model has been evaluated and all these, good things, then we're gonna deploy the model. So just before we deploy the model or while we're deploying the model, we can go back and investigate how explainable the model is. So to start with some big ideas, big concepts, this is where we stand so far because we're about more than halfway through this course. So we've seen machine learning models, we've seen algorithms, we know about the data, we know about evaluations, metrics, indices, indicators, all those things. And up to this point, actually we get also to practice a little bit. We create our own models. So this was a big chapter too. So up to this point, a lot of the things we have is really still data driven. So the model predictions are still heavily influenced with the data we have. And as we've seen before, we know how to build models and we know how to build them and they have high accuracy. But up to this point, we didn't really know how to explain that this prediction was arrived at. For instance, if the model predicts let's say ADT of 500. Well, how did you come up with this 500? Based on what? If we have an equation or an empirical model, we can always look at the parameters and we can figure out, if you have input 1, 2, 3, and 4, this is how you combine things together and this is how you have an output. Over at this point in time, we don't because we don't have an equation format. We have a model format. So the goal from this chapter is really we're thinking about main ideas, main principles, some methodologies of establishing explainability. So to start with, well, why do we need to have explainable models? Well, we need to because of the following. When we create a model and we evaluate this model, and we're confident or we're comfortable about how good the model is, then we get to use it and we get to use it to predict things. And if we want to believe the predictions, it's not only good to know that the model has an accuracy of 95% R squared or R, those metrics. It's also important to know that the way the model was arriving at this prediction also makes sense to us as engineers plus as the problem at hand. In real life, and you'll be surprised for this, a lot of the predictions may align with physics or mechanics or may not align. What I like to always say is they rarely do, especially if you go with a hardcore data-driven model. If you're doing something like a causal model or like a physics informed model, then this becomes much, much different. My main concern at the moment is with data-driven models. So if we know another thing, and I think I've touched upon this like in one of the early recordings, probably chapter one. If we know how a model, if we can see that the model has high accuracy in predicting something, and if we can go back to the model and understand how the model was able to predict this something, then we have new information that allows us to predict this particular something. And this information, since the model is highly accurate, may exceed the information we have now, whether it's based on an equation or a numerical model or something else. So it becomes interesting to understand how, because usually the models we have, even the statistical models, we tend not to see very, very accurate or highly accurate models, as especially if you compare them to ML. Mm, So, of course, here is where we're going to have to talk a little bit about explainability as well as interpretability. And at this point in time, unless you're like a computer scientist, then these would mean different things. For us, there is a lot of back and forth. We kind of use both terms for the same thing. But I thought it might be interesting to start with their broader definitions, and then maybe we're gonna stick with explainable models from now on. So when you think about explainability, this is usually used for models that are able to summarize the reasons for some kind of architecture, mainly a neural network. To do what? Well, we understand its behavior. If we know how things work out, we can gain trust. We can believe the model a little bit, as well as we can generate some information about the way, or between brackets, and losing this very lightly, causes of the model decision. Now, explainability also relates to the mechanism of a model, not mechanics, mechanisms of how the model operates, how the architecture operates. So an explainable model basically could have a very, very complex function that we can't really understand, but we can trace a few things about this function. Now, on the other hand, interpretability is, you can really think about it as a little bit more of a general definition here, like a science of comprehending what a model did or might have done. So it's basically we're trying to see and understand this particular model from a determination point of view. For instance, because I have this parameter and this process, I'm getting this output. So you can see the difference is highly technical. And for our cases may not be something that we can spend a lot of time, unless you're doing some research on it, then it becomes very interesting at that point. But for the sake of a first time you hear about these terms or like these concepts, let's simplify it a little bit. And we're going to say, when we have a model and this model has been seen to work well, we're just trying to understand how the model arrives at its predictions. How does it get to those, class A, class B, those numbers, and so on. Another way to visualize this is actually, if you think about a computer vision model and you're trying to see cracks, why would a model identify a crack as a crack? Why wouldn't it like identify something else as a crack? Or how does it know that this is actually a crack? All of these things are, fall into this chapter. So one of the things here that I usually find, tables to be easy to read and visualize. So if you think about a simple mathematical model or a statistical model, like linear regression, logistic regression, these tend to be very easily understandable, because you're basically saying, you have x1 plus, I don't know, 2x2, and so on. So you can see the relationship between the parameters. Most likely for linear models, something like this, you're going to have a lot of additive, a lot of 1 plus 1 plus 1. There is a lot of additions there, additive nature. These are mathematical based, and we don't, because it's easy for us to visualize and see, we don't really have to explain them. Basically, we have a slope, we have an intercept, we have an error. Once we start to go for machine learning models, this is where things become a little bit interesting because for machine learning, some models are very, very simple. Uh, some are extremely simple actually, and some not that much. If you have a decision tree random forest, you can visualize a tree like we saw in chapter 4. If you have a key nearest neighbor, you can always look at the neighbors or neighboring point of a prediction and see like if it will it fall into class A, class B. So explainability may not be as necessary as we think it is, but once you start to go to more complex models, neural networks, GPTs, SVMs, then it becomes very, very hard for us to visualize and understand. And this is where we have to have some form of explainability. So you're gonna have to come up with a method or use a method that actually goes back to the model, breaks down its structure, and we can see what's going on there. Okay, so hopefully this covers why do we need explainability, and also emphasizes the interesting notion about having simple models, because if you can find a simple model that has high accuracy, low energy expenditure, explainability, basically you almost crossed all these boxes that the one we're looking for. But sometimes simple models may not work as well as a little bit more complex models. And for complex phenomenon, you might want to try both, and there is a good chance that you might end up with a complex model. What I also would like to emphasize is the following. Sometimes we think a phenomenon is complex, but once you put numbers and start to try algorithms, you find that the simplest algorithm can actually solve it very easily. And sometimes we think a phenomenon is very, very simple, but once you start to try different algorithms, you see, oh, we have to use one like very large or very complex model. So it's not always intuitive to know what we need or where we go from there. So the main item behind, at least when I started to think about like this is very personal. When I started to think about explainability was the following. And I don't think I had the right mindset at that time. I thought explainable models mean it tells me the phenomenon, how does the phenomenon take place at that point in time. And I mean, it's really not, it's not that this is the right way to do it. But I think it more of gives you information of how the algorithm itself thinks and come up with predictions. It doesn't really relate to, or as much relate to, how the phenomena take place or how the phenomena happen. Sometimes the way that the model work out to predict a phenomena with high accuracy could mirror how the phenomena actually occurs, but it doesn't have to. It doesn't have to. This is the thing I'm trying to get at. Not every time you see this, it means that this is why something happens. And we'll see examples. We'll see a few examples along the way. So my main item was really this. I'm trying to discover something new. I'm trying to see something in the data that allows me to predict something very, very quickly. More importantly, highly accurate, more than the methods we have so far, let's say in building codes or empirical analysis or simulations. And by doing so, I can go back to the simulation. I can go back to the information I have, maybe the empirical models I have in building codes, improve them, make them better. Okay. So when it comes to explainability, there are many, many different methods. And I think most of the literature, they define them by type. So the first thing or the first type is nature. So you have models that are intrinsic, which means a model itself is simple, a tree model, K and none. And we have post hoc models or post hoc methods. And these ones, once the model is verified and once the model is built, you can apply these methods to explain how the model arrives at its prediction after it was completed. So it's post hoc, after it was completed. Okay, so we're trying to visualize. Yes, mapping is a good term. We'll see it here soon. We're trying to see how the inputs and features map together. We also have other types, for instance, model agnostic and model specific. Model specific is easy. So basically, this is a method that can only be applied to a specific model or a specific type of model, a specific architecture of a model. Model agnostic is something that can be applied to any machine learning models. So if you think about us, CEs, we would like to see something like this, something that we could use for different models. Having this here is not bad, it's good actually, but it just limits us to using this specific method for this specific. We also have scale, so we have models, we have methods that can explain a single prediction, and we have methods that can explain the whole model behavior. So if you're thinking about you have a model and you would like to see how the model in general gets to get high accuracy, you can try global methods. If you have one specific instance where you would like to visualize how this particular prediction was arrived at, this is where we use local method to explain a prediction or a single prediction. And this actually gives me a very good segue to go for talking a little bit about the philosophy of engineering. Because I think the linkage is always in our, in the back of our heads, but we don't like see it related that much. At least in my case, it took me a while to relate these to ML. So in engineering, whether civil or environmental or even other types of engineering, we usually have fundamental methods. You can think of these as statics, mechanics, theoretical analysis, maybe even empirical analysis. So basically, if somebody would say, "Well, I'm gonna design a beam, and I'm gonna make this beam deficient in shear, so when I go and test it, the beam will fail in shear." This makes a lot of sense, right? If you go and test the beam and the beam doesn't fail in shear, you're gonna be surprised because we're forcing the beam to fail in something. We're lacking stirrups, but when we go and test it, it doesn't fail. So we're gonna have to go back and. So what I'm getting at is the following: we usually prep things because we have a hypothesis. And because we're prepping things, then it becomes easy for us to see where they're going. So we would like to know how something happens. And this is why a lot of our methods actually are in equation format. Because we could see the parameter, we could see the relationship between the parameters, we could see the relationship between the parameters and output. So a method of investigation or engineering investigation is usually tells us the relationship between the predictors and the response. In reality, in machine learning, this may not be easy to get, especially if you have a complex model. And actually, even if you have a simple model like a decision tree, it doesn't really tell you the relationship. It just tells you the splits of data. So unless you really have something that can tell you the relationship exactly, then it becomes a little bit interesting because if you think about it, we have a model that works very, very well. We don't know how the relationships and we don't know how it works, but it works well. How do you justify this? So this brings me to this. Machine learning is fundamentally different than engineering, or the method that we use in engineering. Because in our methods, we can really see, M equals FYZ, M equals AS, FY, D minus A over 2. Everything is given to us, section analysis. In ML, use this as many data as you'd like. It's going to be very, very hard to get that functional format. And it makes it a little bit also, I don't want to say concerning, but it makes us think, like, how can we trust such a thing when we don't know how it works? It works, but we don't know how. So what we like about equations, or what we like about our methods, is that they're simple, they're universal. M equals FYZ and almost everywhere. Doesn't matter where you come from. They tend to have some reliability, especially like if you're thinking about the building code context. We have a lot of reliability. We have data and we have things. They're very, very intuitive. Fy times z, you multiply strength times geometry, you have capacity. Very easy. Transparent, you can see them. You can see the relationships. One of the most important things they're usually accepted across, everything. And whenever we have those empirical ones, we tend to update them. This is why building codes tend to be updated because we have new information, we have new tests, and such. ML is different. ML is universal. We can add reliability, it doesn't have to. Sometimes it's intuitive, many times it's not. Sometimes it's transparent, many times it's not. Acceptance in our community is growing, not fully there yet. And this is tough. We tend to update them, but not on the scale of a building code. We don't have committees for this. We have a few committees for machine learning, but we don't have something that we can embed in building codes, and we start to think about those. And this is why, learning about ML becomes something important for us, because the future is going to be here soon. So when we think about this, we would like to learn how models work, because it makes our life a little bit easy, gives us confidence. Also makes our communication better, because if you think about, communicating with owners, with different engineers, with building officials, it's going to be hard for them to agree on something if they don't know how it works out. Like, for instance, a very true scenario is you could be consulting on a project and give you the data and the model, and the model would say, you know what, use a column that's 16 by 16. So you go and you put down in your paper 16 by 16, but the engineer would like to know, or the building official would like to know, well, why was it 16 by 16? Where is the capacity? Where's the detailing? Where are the other things? Coming back to them and saying, well, you know what, my model gave me 16 by 16. Got it, right? Because remember, with CAE, there is a lot of human component. You're building structures for occupants, for people, for many times, weaker societies, weaker communities. Sometimes we don't have funds, so we have to be extremely cautious, extremely careful. So trust is a big item. And trust is a big item because people will be using your designs. And at the same time, trust is important because of many, many other things, but also meshes well with this item. When we think about, weaker sections or forgotten sections of our societies or like communities, what's dangerous is, and I'm using dangerous here intentionally, is that because there is a lot of the component on machine learning has data, we don't tend to have as many data as we like on specific sections of our communities, like let's say neighborhoods or occupants or uh, let's say people with special needs, because most of our design are tailored for able bodies. For instance, I had my student Haley, she was doing evacuations for disabled population. And if you look at the literature, there is very, very small amount of research, very, very small amount of data. Even the experiment we did was a full building, but we only had like a very small percentage of occupant that would fall into that portion, and made it very, very hard. And somebody would think, well, how are you going to use machine learning in this case? How are you going to use machine learning to show how a specific population, for instance, behave, accurate and stuff? And the answer is, without having enough information, it's going to be very, very hard. Very hard. We need a little bit more data. So it also gives you the intuition when we have small data and we don't know how the model works out. So it becomes a big item. So fairness is a big item, inclusivity is a big item. Having data that showcases these two things is also important, critical. So what are we trying to do? Well, let me give you two scenarios, and hopefully these two would mesh with you nicely. So let's say the most intuitive scenario is you have a model and the model doesn't work out as well, doesn't give us good prediction. Well, without knowing how the model arrives at the predictions, we can't really go back and fix the model. Because if the model keeps giving you wrong predictions, while you know that you have a large data set, while you know that you have followed the best training and verification process, the model still gives you wrong predictions, and hence you have to ask yourself, well, why? Without explaining the model, it's going to be very hard to know why. The second example would be the following. Let's say the model does give us good prediction, but we don't know how. Now, let's say the model gave us good predictions, but its explanations are not good. Let's say we explain the model and we see that the explained or the explanations from the model do not match with physics, do not match with our domain knowledge, do not match with mechanics. Well, what are you going to do? you're gonna have to think and say, okay, well, the model works well prediction-wise, but it's the way it predicts things doesn't match what I know from physics or section analysis. Let's say when we all know that the moment capacity for a W shape is, let's say, FYZ, right? Let's say we created a machine learning model and we, explain the model. And somehow, for some reason, the model says, well, you know what? It's really, this is the relationship the model found. Fy divide by z. And you're going to have high accuracy. Let's say you have very, very high accuracy. Well, what do? Are you going to go with the model, or are you going to have to create a new model? Well, these are some of the questions that you might have to think about. And of course, this would be a bad example here to keep without actually classifying what it is. So some of the methods we use to explain models, I'm going to go through over a few of them, but so the math behind it can be complex, very upfront, and I don't think it's that hard to know the math, but I think for the sake of this presentation, for the sake of this recording, I think it's more important to discuss them in general, because what I do in class, if you happen to be a faculty member, so each one of those methods we describe, and we actually do the math behind them. And usually each method takes about maybe a lecture or half a lecture, so it takes a lot of time to do the math. However, I think the best source of action, course of action for this chapter, is we describe these in general, and we explain what they are. And if somebody is interested, you could do the math, on the side. I don't think my book has the math, to be honest. I think it has the math for some methods, not for all of them, because some of them can be dense. Plus, you can easily find them, on different sources. It's not something that's extremely detailed. Extremely unique. So one of the easiest things somebody would think about explanations is go back and simplify. When we have a model, we have, let's say, 5 features or 6 features. And the first question that should come is, if you would like to explain a model, you would say, well, which one of these features is actually contributing much to the prediction? And this is what we call feature importance. Feature importance basically tells us that we analyze the features and we identify the one or ones that contribute almost all the time to the correct prediction. So for instance, we have this example here. We have feature 1, 2, 3, 4, and 5. And as you can see, feature 1 has an importance of 100%, which means out of all the predicted values correctly, feature 1 was always there. You can see feature 5 has very, very low importance, which means we can actually get away without having feature 5. Now go back and start to think about how does feature 1 actually meshes with physics or mechanics and all those things. Is it essential? Is it something important or not? So this is also one way to figure out explainability. And if you remember our discussion on feature engineering, feature selection, this is not feature selection. This feature importance happens after the model has been predicted. Feature selection happens before that. So the difference is substantial. When we're dealing with feature engineering, somebody would say, I'm going to have feature 2 divided by feature 1 as a new feature. Well, now the model doesn't understand feature 1 and feature 2. It understands the new generated feature. And you're going to have to realize that is this new generated feature is actually important or not. So how does feature importance work? Well, think about it this way. If you have a model and the model always predicts the values correctly because you have feature 1, then feature 1 is important. And if you would like to test for that, well, take out feature 1, remove the feature. If when you remove the feature, the accuracy of the model goes down, the accuracy goes down, this means that this feature is important because the accuracy suffered, or we have loss in accuracy. If the accuracy doesn't change, then maybe the feature isn't that important. If the accuracy increases, then we have to have that feature. Now, in reality, we don't just remove features. What we do is we alter the features. So sometimes you could change the values of the features. You could change the order of the features. And all of this is called permuting. So basically, we're trying to change a systematic change of different features to identify the ones that when we change, we see a loss in error. I mean, a loss in, an error in predictions. So the emphasis here is important. We're tying explainability with model accuracy. So basically we're saying if the accuracy of the model goes down, this feature is important. In reality, accuracy of the model is just one thing. We also have to think about like what's the relationship between the feature. Maybe one feature on its own has less importance, but this feature work out very, very well if you have other features next to it or with it. And this is where feature importance it's a simple way to figure out explainable models, but it also suffers from other things because it doesn't take into account relationship between features or the influence of one feature on other features. So we have to be, as always, it's a good way, but we have to be careful with the negatives. So everything has positives and negatives. Another way is what we call PDP or partial dependence plot. So partial dependence plot, what it does, it's a plot, it's a scatter plot, and it shows us something like this. This line, this is the feature or quantity of feature, and this is the target or the outcome. Basically, it shows the relationship between the quantity of feature, the value of feature with the outcome. And in this case, it would say something, you know what? At this point here, it doesn't seem that if we change the value of the feature, the target doesn't change as much. It's almost constant. However, in this range here, if a small change in quantity of feature tends to give us larger changes in target. So this could help out because we can now see the relationship between the feature and target. In this case, we don't know what the relationship is. We just know that there is a relationship. And this relationship could be linear, could be nonlinear, could be complex, could be something else. However, just like everything else, we have positives and negatives. And in this case, the negatives is we keep all features constant and we only change once. Another negative is that we are assuming that the feature does not correlate with other features. And they could correlate or they could have some form of relationship. So in one way, now we can see a new relationship, linear, nonlinear, but we also ignore the other benefits. Well, somebody would say, why? Why don't we have other methods? Well, we do. You will see them in the similar to PDB. We'll see them once we have a PDF. And just PDB is the one that we start with. Yeah, one more thing. PDB shows actually the average influence. So this is one key number too. The average influence of one feature at a time. So we're only varying one feature each time. We're not varying everything at the same time. We only show the average. So the average could give us interesting results depending on the problem. Sometimes it doesn't. Of course, we also have CHAB. By now, I'm sure a lot of you have heard of CHAB package or Chabli values. So this is a little bit much more complex, and what it does, it's really based on an older game theory approach by Chabli. And this is a unified agnostic method, so it should work. I think by now it works with almost all algorithms, or a very, very big percentage of algorithms. So there's a very good push to make it agnostic. What SHAP does is it actually simplifies the problem a little bit, but in a very interesting way. What it does is we take a feature, we give it an importance value, and then we iterate over all possible features and all possible combinations to ensure that we account for all the interactions. Now you've heard me say it all 3 times, which means this is going to be a very, very time-consuming and energy-consuming method, especially if you have like a massive data set. If you have a smaller data set, many of our data sets are not that large. If you have a small data set, then it's not that computationally extensive or exhaustive. It's fast, but for very, very large methods, I mean data sets, it becomes tough. Too much math. And Shabli gives us a lot of nice visualizations. For instance, in this case, we have different plots, and we can go, say, plot by plot here. start with this one. This is what we call a summary plot. And this is a little bit interesting to visualize. So let's go through this step by step. So here we have Shapley values. So these are the values from Shab. Here we have feature values. And this goes by color, doesn't go by numbers. So usually low is blue, high is red. And here we have the features. And usually the features are ordered from highly important to less important. And this one says the following. If you have, for instance, this is a binary classification problem. What it talks about, this is Bashiti's research, actually. So if you have a concrete mix or a concrete specimen, and you heat it, we're trying to see if the concrete will spawn or not. So spawning means cracking or severe damage. So here it says if you have PP fibers in your mix, then the chances of spawning is low. And here's why we have the blue. So low values of PP fibers give us less chances to spawn. Higher values, red, of PP fibers pushes things to spawn. Moisture content. Let's see, moisture content is usually easy to visualize. If you think about moisture, if you have a lot of water in the concrete, as you can see here, this is high amount of water, would cause things to spawn because the right side is spawning. If you have less water, as you can see here, bluish, this is where we have less spawning. So more spawning, less spawning. Did I mess up the first one? I mean, let's go back and see. Yes, oh no, low values, PP fiber will spawn because we don't have enough of it. Higher values, I think I messed up the first portion of the recording. When we talked about PP fiber. If we have more PP fibers, we have less chances to spawn. If we have less PP fiber because we don't have enough of them, we have more fibers to spawn. And you can also see somewhere, let's see, let's do another one here, heating rate. So heating rate, is also easy to visualize. If your temperature is low, not that high, then we have less chances to spawn. If the heating rate is high, you can see here some red, it has more chances to spawn. What's also interesting here is, as you can see, you have some blue here under spawning. So this tells us that for some specimens, if whether you have high heating rate or low heating rate, you'll also have spawning. And this is where things become interesting. Same thing for standard binary ratio. For some specimens or some mixes, whether you have high value, high standard binary ratio or low binary standard ratio, it's not going to spawn. So how do you get physics out of this? It's going to be tricky. Hopefully the shooter will figure it out by the time we finish up this recording. And of course, you can see some cases here, some parameters that have very, very low influence. So basically, they don't affect that much. Here is where you can see for one particular instance. So this is for one particular mix. The figure shows us if PP fiber adds 1.5, this one adds 0.041, 0.66, and we add these up to come up with the predicted value. And this figure here is the same one as this one with this one there. Now, the interesting thing is these are all Shapley values here. This is the base value, this is the other Shapley values, and this is 0. And you have, more chances to spawn, less chances to spawn. So you can not only know the final prediction, but Shapley can also tell you the contribution of each feature or of each parameter to the prediction, which is interesting. However, we have to remember, this is how the model analyzes the data. This doesn't mean that this is how the model analyzes the phenomenon or the physics of the problem. This is a very clear distinction. Now we also have another method. We have surrogates. Surrogates can be, I know some people might not like them that much. I have a little bit some ideas and thoughts about them. But surrogates, they're good to know. A surrogate is basically a secondary model that we train to replicate the behavior of a much, much more complex model. So we have a complex model, too complex. So what we do is we train a surrogate to become a proxy for the bigger model. And this way, predictions from the surrogates when you predict a surrogate, let's say you have a very, very complex neural network, and the surrogate is KNN. Then instead of focusing on the new complex model, you would say, well, I'm predicting this value from the surrogate because I can see that the neighboring point have contributed this much. Now, somebody would say, well, if this is the case, then why didn't we just get rid of the complex model? Why don't we just rely on a surrogate? Well, without the complex model, you won't have a surrogate. But this is also a good chance for us to always start with simple models. And when things fail, we go for complex model. In all of these cases, all of the methods we have so far, there is a very big emphasis on that. We're relating highly accurate models with high explainable models. Or also sometimes what we do is we say that this model is explainable because its explainability gives us high accuracy. Again, I'm trying my best to continue to enforce this idea. Maybe enforce is the wrong term. Reinforce this idea. We have to distinguish between accuracy as well as, model that work due to physics and other things. Also, we have some methods for unsupervised learning. You'll see these in a little bit in the PDF. Actually, we can just go in right there. We have polar lines, we have explainable trees. But let me bring in my PDF. I know the chapter is lengthy in the PDF. Let's see. Yeah, we've covered these. Yeah, remember, accuracy is one way to look at the model. It's not the only way to look at the model. So explainability, interpretability. The goal is really trying to do this. Our goal is trying to create a model that we feel comfortable with. It can capture the property or the problem, which means good accuracy, and it can explain it well. Hopefully something like can match with our physics or something that can match with our domain knowledge. Because if you end up with a problem that has high accuracy, but it doesn't explain things the right way, or at least as close to how we know things happen, that could be an issue. Yeah, we talked about those. Oh yeah, this is good. So up to this point, even our literature, unfortunately, we have a lot of papers on ML, which is great. However, a good portion of these papers tend to be tend to simplify the process a lot. Like for instance, collect data by algorithm, you have a model, end of story, right? This is like the basic way to use ML. I think we can gain much, much more by, trying to learn more from the model, explain the model, maybe try different types of models versus just, collect data is an algorithm or a number of algorithms. And we have model. Think a little bit more outside the box, I would say. Another thing that is important, and I think we've touched upon this a little bit, the degree of explainability also differ from one person to another, from one engineer to another, from one stakeholder to the other. So you have to be mindful. Like for instance, when you look at Shapley's values, to you it might be something easy because you know what it is by now. But for somebody else, they're gonna question what is this Shapley thing? Like why doesn't the model just tell us how it works without having to go through surrogates or Shapley values or feature importance? That'd be great if we could. It's a little bit much more complex than that. And I have a few thoughts here. I don't know if they're helpful or not. Maybe for a faculty member they can, or a senior engineer. So basically, when we think about intuitiveness, it takes a little bit of time to get some intuition about let's say about machine learning and engineering. And the transparency becomes a little bit easier to visualize once we know how things work out, instead of just this is a black box, this is how it works. Acceptance usually happens a little bit later. Like once things are much more established, once you have building committees on things. So I'm hoping, or we're hoping that intuitiveness and transparency are things that we can solve ourselves, like by practicing, by learning. And the third item, acceptance, will come with time. Just needs a little bit of time and push. Fairness, inclusivity is always a big item, so you have to be careful of those. Feature importance, the degree to which machine learning model realize, yeah, good. We know what this is by now. We know what PDB is. Oh yeah, this is a good example, and this is a little bit away from my famous examples on beams. Let's say here we have a very expensive chemical compound, for instance. I don't know, maybe to uh, whether it is to have, cleaner water or like to paint on something, or it does something good for us, but it's expensive. Somebody would say, well, instead of things going, let's say the outcome is going to be binary, so maybe the outcome is somewhere here, unsafe safe. So if you look at this, let's say gap here, this portion, you can see that this line is all, or the PDB is almost horizontal, which means that even if you add more from that material, you're not really changing much of the specification from not safe to safe. So you could basically cut some cost off by only using this value here and not having to add much more of this chemical compound because it costs so much, right? So this could be one way to think about PDB, but also remember this is also some of the limitations of PDB, average values, no relationships, or the assumption of linearity between relationships and relations and stuff. So to overcome some of these limitations of PDB, we also have what we call ICE, or individual conditional expectation plots. We also have here ALEs, accumulated local effects. So all of these are trying to add a little bit more to the limitations of PDBs. I'll show you these soon. We've talked about CHAB, and you can see it's going to be a very iterative process because you have the summation there. We also have LIME. So LIME is a local interpretable model agnostic explanations. So LIMEs usually work on the local level. So you take a prediction, you break it down by using linear assumptions. Surrogates, unsupervised learning. We have explainable trees. So basically, once you have things into clusters, you could use explainable trees to say, okay, well, for this cluster, I have these features. This is the samples. This is the values, and then I can break it down to other clusters. Polar lines are something like this, where it would say you have the different features here, and this is, for instance, cluster one, and the features on the tree or the plot for cluster one tend to realize these values from these features. So this would be the map for cluster one. I'll show you, I have a few examples more. So this is, we've all seen data robot by now. We know how to use it. We've covered that in the previous chapter. But if you go all the way to once you add your data, if you go here to show advanced options all the way at the bottom here, and you go to additional, this is where you get to choose tab values. So the option is usually turned off by default. You can turn it on, and then it will list out the models that have tab in them, and then from there it becomes, you can just plot them and see feature importance and all those things, just like, for instance, let me show you here. We have, yeah, like for instance, this would be the feature importance using chat for this particular problem. You can see, for instance, feature A, which is the distance between the moment of loading and the boundary condition, substantially important because the problem is bending. So it depends a lot on this moment arm. You can also see PDBs for the different values and different features. You can see model size, prediction time, sample size, all those information that could help you later on. I think this one here, yeah, we're comparing different models. And the interesting thing, once you start to train different models, it becomes interesting because all of these models, they have similar accuracy, but as you can see, the way that they label features as important or not is not the same. they all agree A is important, as you can see. However, for instance, for F, for E, for T, some of the importance values are not similar. Sometimes they're even completely different. Like, look at E. For E, for the Kira's model, it's about 15%. For the other two models, it's very small, like 2 or 3 percentages. So this makes you think, how can three different models with similar accuracy each give us different feature importances? It's because each one of those is based on the architecture of the model, because we're using the same data. So whenever you do this, it's no longer a data problem, it's an architecture problem. Same thing with PDBs. Exactly. You can see some resemblance, but not really. Especially here in this case, whenever the values are small or smaller moment arms, somebody would agree that we have similar resemblance. But for larger moment arms, it's substantially different. Yep, same here as well. So compare. This is why my advice is always to try to compare different models and different examples as well. This is completely different. Yeah. These case studies were interesting to build. We have all this data, by the way, on the online platform. You can just download them and train them, play with them. My advice is always to try to have some practice, just like what we did in the previous exam, in the previous recording. Apply some data and try to go from there. Okay, so this is data IQ. Let's see if I can go a little bit further. Yeah, we've seen this in the slides. Yeah. So for instance, in this case, these are all PDBs. The red ones are the averages. So this is what you would naturally see from a PDB. The blue ones are the ICEs. These are each individual observation its own line. This is why it's called ICE. The red one is the average of all those things. So whenever you try to analyze something, it's easier to look at the average if you're trying to look at the global behavior. And if you have like interest in one particular point, you can always look at its own ICE. Yeah, local explanations, we have those. This is how Lime looks like, by the way. So Lime would say, for this particular instance, the probability of the specimen not to spoil is 84%, which means the probability of it spawning is 16%. Now, how is that? Well, for spawning, it has less moisture content, so that's going to be 12. Add 9, add 6, add 6. This is how you come up with values. This is the other way, collect for not spawning. So you can easily accumulate those and see the differences for all those things. Also, we have here the codes, the Python codes for the problems. You see here, this is all Bashiti's work. Feature importance, by the way, this is how it looks like. Yeah, this might be something simple, but some packages gives you relative importance, so with respect to each other, sometimes gives you like absolute importance. It's very easy to navigate these two things. We also have correlations here, so this is not different. We have all those different visualization tools. I want to go all the way to the end of this chapter because I have pictures of the tools for unsupervised learning. Different problems. Okay, here we go. So for instance, this would be the explainability for a k-mean, for k-means. We start with all the data and then we try to split down into different clusters, and each cluster, as you can see, has its own color. So this is how we split out. Like you can see here, class 1, cluster 1, or class 1, class 3, class 3, class 3, class 4, class 3, class 2. And you get to combine them together eventually. Yeah, different trees for different clusters. Here is again, you can see the types of clusters and how each cluster relies on specific features. And if you look closely here, I'm hoping this would be clear. But if you look at this orange cluster, This is exactly like this purple cluster. This one here also is similar to this. So both clustering algorithms were able to arrive at 4 clusters, and the 4 clusters match almost identically, except the way that they were plotted is just different colors, but the clusters themselves, they match. So this is a little bit gives you some confidence because now you have 2 algorithms or more that all behave similarly. In the previous example, the one we used for data robot, we tried different algorithms and they all have good accuracy, but they don't match when it comes to feature importance. Which means if an engineer creates, let's say, one model, their response to a question would be different than another engineer who has 3 or more models. Because the more models you have, the more it becomes easier for you to visualize the differences between the models versus relying only on one window to model behavior. Conclusions or explainability is important. We need to know it and we need to know the limitations. Yeah, you'll see a lot of the questions here where they relate to go back and do this problem, go back and do that problem, or like use this data set to do this problem. I think these are practice is very important. So when it comes to the recordings here, it's I tried to like to do all the problems, but it just took I think a few hours each time. And I ended up having, you know what, this is just not gonna work. I don't think it's gonna be beneficial to have, you know, a 3-hour video on how to use softwares. But I think what we did in the previous chapter was good enough to try a few things maybe one time, and then you can train and practice more on your own time. And in between, if you have any questions, just you know how to reach out to me. I'll be more than happy to help. Practices. And think of this as statics. You know, you're gonna have to really put some practice into it. Chapter 8 is next. Okay, we'll come back to chapter 8. Until this point, thank you all, and hopefully I'll see you very, very soon. Thank you.